All right, so this is lesson 1E, as you can see. And basically, you already know everything that I'm going to cover right now. It might be called different, but still. For example, we're looking at centers of triangles last time. We know that, for example, for the perpendicular bisectors, what is the point of having all perpendicular bisectors in a triangle? Well, that gives way to the center of a circle that surrounds the triangle. So basically, and it's called the circumcenter. That's basically one of the things that you need to keep in mind. All right then. So this is called the point of concurrency, because that's where all perpendicular bisectors meet. Guess what? It could the lines, the perpendicular bisectors can intersect inside or outside, as is the case of the obtuse triangle. See that? Okay then. Now let's go with the angle bisectors. Look at the angle bisectors. So you already learned how to create your angle bisectors, and when you look at all three angle bisectors, the point of concurrency, right, is called the in-center. Okay, in-center. And why is it called the in-center? Well, hello, it is the center of a circle that will fit perfectly inside the triangle. Now the in-center will always be inside the triangle. Duh. The circle is inside the triangle. This is what we call an inscribed circle. Okay, it's inside, so the center has to be inside the triangle, unlike the perpendicular bisector. It could be inside or outside, it doesn't matter, because the circle will surround the triangle. It will be circumscribed. Okay then. The medians. Well, the point of concurrency is called the centroid. We already went through that, okay? But what's so peculiar about it? Well, that this point right here of concurrency, okay, yes, it is equidistant to the sides, but that's really not the purpose of the lesson. The purpose of the lesson is that you notice that this length right here is twice as much as this length right here. Remember, we're talking about the medians. So every time you want to draw a median, you have to calculate the midpoint, which basically you have to use the perpendicular bisector. And once you create the midpoint, you connect it with the opposite vertex. Midpoint, opposite vertex. Midpoint, opposite vertex, right? So you know, 12, 12, 8, 8, 10, 10. Midpoint, 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 midpoint. All right, so the segment that goes from the vertex is always twice as long as the segment that goes from the concurrency point to the side, okay? Now let's take a look at an example right here. Okay, so this is a problem that I found. It says that in the diagram below, right, TB is 9. TB, where is TB? TB is 9. Okay. They want me to find the length of TD. TD, they want me to find this length right here. TD. Today. Okay, so I need a ruler. So let's see now. The whole TB is 9. So TB equals 9. Okay, so they want TD. What do I know? And unfortunately, this is where we start with the, I guess, the algebra. I know that this is twice as much as dB. I don't know what the lengths are, this and this. All I know is that this is twice as much as this one. So what I'm going to do right now is I am going to call this 2x. And you know what? Forever and ever and ever. And I caught you. Forever. This is going to be 2x and this is going to be 1x. Okay? Cool then. And not only that, the whole length right here is 9. So I know that, something like that. Okay, the whole thing here is 9. So TD plus DB is 9. So let us talk geometry. TD plus DB equals 9. Remember, they want the length of TD. Okay then, so now let us replace. I know that TD is twice, okay? TD is twice as much as DB. So this is 1x. When you add the two segments, you're going to get 9. You add them up because they're like terms. If you have 2 x's and you add one more x, you're going to have 3 x's. Common sense. Okay then. Now, according to the laws of solving equations, 3 is multiplying x because it's 3 times x, it's 3x. So what I'm going to do is I'm going to divide by 3 on both sides. Okay? And when I divide by 3, 3 divided by 3 is 1, 1x. 9 divided by 3 is 3. X is 3. To begin with, let us see what x represents. X is dB. Ah, okay. Hey, wait. dB is 3. TD is 2x. X is 3. 2 times 3. Wait. So basically TD is equal to 2x. In this case, 2 times 3. Hopefully you won't forget. So TD is equal to 6. Okay. So that means that dB, since it is x and x is 3, dB is 3. And it makes sense. This segment TD is twice, okay, 6 is twice as much as 3. So there you go. There you have it. So we found the length of TD. Please don't ever forget that. So that was the example. Oh, okay. So altitudes. Okay, we already went through altitude. What do we know? Okay, so the altitude is a segment that goes from any vertex perpendicular to the line containing the opposite side. This vertex, line, segment, opposite, perpendicular, you see, 90-degree angles. Vertex, perpendicular, vertex, and perpendicular. The point of concurrency is called the orthocenter. So we're good. Now, the altitude can also be, the orthocenter can also be inside or outside the triangle. So right now we have two things that can be outside the triangle. We have the orthocenter and we have the circumcenter. Perfect. Let's move on. Okay, so now we are going to look at this problem. It says, for a triangle, which 2 points of concurrency can be located outside the triangle? Well, hello, we just discussed that. The circumcenter and the orthocenter. Alright, inscribing a square in a circle. Draw a circle of any radius and let's get started. Sure. Okay, now, for my class, if you do this before I do it and call me up, then, and you say, Becker, pull up, then I will grant you 2 points on your grade. So draw in a circle. Okay. Draw in a circle. Now, how do I construct a square? I don't know. Okay, so this is the center. I know. Let me call this circle O. So what I'm going to do is I am going to create a diameter. Okay, now after creating that diameter, what am I going to do? Well, a square is a polygon that contains 3 congruent sides. I mean 4, sorry. Ooh, what am I thinking? Okay. Oh my God, I need this to be the same length as something else. Now, what if I draw the perpendicular bisector? perpendicular bisector will always be equidistant from these 2 points. So therefore, it might have the same length. It will be radii. There you go. I'm gonna construct the perpendicular bisector. Okay? So how do I construct the perpendicular bisector? You could either follow the steps of constructing your equilateral triangle. Okay, create a circle here, right? If you want to label this, you could label it. I really don't want to label it, but AB. So you could follow the steps of constructing the equilateral triangle as you have already learned. And please don't forget. Or you could follow the steps of that you already know. That to construct the perpendicular bisector, you only need more than halfway. Okay? So it depends. I mean, and it's fine and it's useful because sometimes you don't have enough space in the paper to follow the equilateral triangle. As long as you know that, it always works. Why is it that every time I'm recording my phone rings and then it screws my plans? Okay. So that is my perpendicular bisector right there. The line that joins these 2 points of intersection. Remember, these are circles. Okay, now let me follow the steps of the equilateral triangle to show you that it is the same thing. So I open the compass to the length of AB. And I construct circle A. And then with the same radius, I'm gonna construct circle B. Okay, it doesn't matter. Now I just have to join the points of intersection. So I could do this or I could do this. You see that it's the same thing? See it? Cool then. But that's only for the perpendicular bisector. If I ask you to draw a equilateral triangle, please, you know what to do. All right then. So what else is there to do? Nothing. You already know that this is your main circle. Right here. That's your main circle. So all you gotta do now is just go to the point where the perpendicular bisector intersects the circle and connect the points. That's your first equilateral triangle. Guess what? Let me see, that's the circle, so it should be right here. So, and guess what? That is your square. Like this, square. Haha, you thought, right? Okay, let me model it again just so we can be sure. This time I'm just gonna do it with the pencil. So, what it says? Draw a circle. Now, with the compass, you should already know. Oh shoot, sorry. Okay, here we go. Okay, with the compass, you should already know what to do. And you should know where the center is. I could see it right here. See it? Because the compass punctuated something. Okay then. So now create a diameter. Does it matter how you create your diameter? It really doesn't. Look, this is gonna be my diameter, my new diameter. Just for the sake of doing it. My new diameter. And now I'm gonna construct the perpendicular bisector. So I open more than halfway. Okay. I go to the other point B. Okay, with the same radius, sorry, and do this. And now I connect the points of intersection. And last but not least, all I have to do is now connect the points. So this is gonna be from here to here. Okay. From here to here. And from here to here. Oh, shoot, I'm missing one side. There you go. And that's your square. So it really doesn't matter how you do it. You see, I did both and they both the same way. Okay then, let us move on to the next construction. Oh gosh, I really don't remember this one, but I'm gonna try my best. So I'm supposed to construct a line that is parallel to this point. So we're gonna follow the procedure, okay, we're gonna mimic the process of copying an angle. So I choose a point on this line. Let's try this point right here, and I'm gonna call it point A, okay? And what is it that I'm supposed to do? I'm supposed to like just connect the points like that, right? Copy an angle. If it's upside down, it doesn't really matter. The process is still the same. So I am going to draw an arc from point A. Okay, that's what I'm gonna call it. Point A. I draw an arc. Now I'm gonna go to point P and I'm gonna draw the same arc because I'm copying the angle. See that? Or you could just, you could just do a circle. It really doesn't matter. Okay then. Now I am going to call these points of intersection. Okay, I'm gonna call it B and C. I'm gonna call this point of intersection B prime because that's the same point as this one, right? Now you're gonna move the compass to the opening of the arc like this. Okay then, cha 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 cha. And then now from point B, because that's where I drew the arc, from point B prime, you kachingi kachingi kachingi. And we're gonna label this point C prime because that's what this point represents. And now guys, I just have to join point P with point C, and that is your point of intersection. Okay? And let me see now. Okay, I don't know what oh, okay, I got scared. I thought this was the point that I was supposed to use. Okay, good. It was just little dirt. Okay, now construct the two tangent through a point on the circle with compass and a straight blah, blah, blah. Construct the tangent to the circle. Okay, they just want one tangent. I thought it was two, but no, they want one tangent. This is just the topic. So one tangent. Okay, so what you're going to do is you're going to create your segment. Okay, it's basically like constructing the equilateral triangle, but I'm gonna show you. So I have this point right here, and what you're gonna do to actually draw a tangent is you're gonna extend the point. Okay, so we're gonna get A B. Okay, just for the sake of doing it. Now you need to have another point right here. So what am I gonna do? I'm gonna create a segment. So with the same radius. So I am going to measure radius AB. See that? Radius AB. And now you're gonna go to B and you're gonna create the same thing. A mark, or you know what? Nah, let's just do the same process that we've been doing since the beginning. You can just create another circle. Okay? It really doesn't matter. Now we know where the radius is the same. AB is the same radius as BC. And basically all you have to do now is between A and C, create your perpendicular bisector. Please, perpendicular bisector. How you want to do it? You want to open up all the way to AC, or you could just go less than, okay, more than halfway. In other words, the compass must, what the compass marks must be longer than AB, right? So it really doesn't matter. I go AC. So basically, now I create my perpendicular bisector. See that? Now I go to C, create another perpendicular bisector, another circle, or arc, whatever you want to call it. I've been saying this for the longest. And now connect them. My friends, this line right here, it's your perpendicular bisector, and as well as the point of tangency. This is a tangent to a circle. What is a tangent? A segment that touches the circle just once. Got you again. So a point that touches the circle just once. Right. Do you want me to show you another example? Sure, because I'm not giving too many examples of this. All right. So you have a circle. Oh gosh. Okay. So we have a circle. Boom. I see the center, so the center right here. So you have the circle right there. Okay? Now, let's say you want to draw a tangent to this point. So I'm going to go from the center, and I am going to, from the center, I draw a segment long enough. Remember, you have to have the same radius. So go to the radius and do the same thing. Mark a point right here or draw another circle. I really don't care what you do. Okay, let's label these points. So this is going to be A, this is going to be B, and this is going to be C. Okay, and now the last step is to construct the perpendicular bisector from A to C. So you could follow the equilateral triangle process or the more than half process. It really doesn't matter. Okay, so I do that. I go to C. I do that. And now connect the points. And this is the tangent, okay? And this is the point of tangency. Now, what's so peculiar? The radius to a tangent, it always forms a 90-degree angle. Cool? Always. The radius, and you see it right here. The radius to a tangent forms 90-degree angles. Now, will I prove it? Of course I will prove it for you. Okay, now let's see. Okay, we have a problem here. So I'm gonna make this model. Okay, they want me to construct the tangent to the arc below. How in the world am I gonna construct the tangent to this arc? Let's see. Oh, I see. They want me to construct the center first. I don't have a problem. You already know how to construct a center. Just create a triangle right here, or not just a triangle, but you only need 2 points. I mean two what do you call it? 2 chords. Now, as long as you remember that the chords must not be parallel, because if you do parallel chords, the perpendicular bisector is always going to be the same. So anyway, how do I find the center of a circle? Easy. Construct the perpendicular bisector of the segments that let's call it the chords of the chords that you drew. So let's have this perpendicular bisector. So and first perpendicular bisector, so I connect the points. Okay, now I go with the perpendicular bisector of this other chord. Now please, if you need to label them because it's easier, you know, like AC, AB. So like that, you know what you're talking about when you have to give an explanation of the steps. Is this more than halfway? Yes. So that's exactly what I'm gonna do. Right here. Right here. I have my perpendicular bisector. And this is the center of your circle. And you already know why. Okay, should I finish the circle? Sure. Although I don't need to, and I'm gonna explain to you why I don't need to. Okay. See that? See that? It's beautiful, right? Okay, so now we know how to find the center of a circle. And I completed the circle, although I didn't need to because this is where they want me to draw the tangent. This point right here. So, how am I gonna do it? Easy. Draw a segment from the center of the circle to the tangency point. And it has to be long enough, right? So I did it long enough. Hopefully I did it long enough. And all I need to do now is go from the center to the radius. Boom, I did. And you know that you gotta do the same thing over here. Oh my God, could you believe this? Just like perfect, but I'm gonna extend my segment a little more. Okay, so I extended. So this is the other point. And you know what to do. We call this A, we're gonna call this B, and we're gonna call this C. And now all I have to do now is construct the perpendicular bisector of AC. if you notice, I'm not gonna go all the way to AC because my circle is gonna go out of bound, okay, out of boundary. So I'm just gonna measure more than halfway, okay? So that's it, boom, right here, okay? And now I'm gonna go to AC, I'm gonna go to C with the same measure, okay, with the same radius. And I'm gonna connect this point right here. And my friends, here you go. The point of tangency. This is your tangent. Okay? Cool then. Let's move on. Okay, so what am I supposed to do right now? Construct two tangents to the circle that passes through point P. Okay, this is different. I am going to show you how to construct two tangents from, so far we have been constructing a tangent through a point on the circle. Now we're going to construct through a point on the circle right here. All the points have been done on the circle. Now we're going to construct a tangent line that goes through a point outside the circle. Well, the process is kind of like the same. Okay, so join the 2 points of intersection. Did. Now, let's label this. What do you want to call it? Let's call it A, so to be consistent. Now, what are we going to do? I think I am going to construct the perpendicular bisector of AP. You already know how to construct the perpendicular bisector. Okay. And now, I'm just gonna connect the points of intersection. Okay, but what the hell? That's not a tangent. That's not the purpose of it. This is actually the procedure. You join the points and you create the perpendicular bisector. Please do that. So we're gonna call this point, what do you want to call this point? B. Let's call point B. So what's next? Easy. The perpendicular bisector makes AB and BP the same size. In other words, BP is also a radius of AB. Now, how in the world am I gonna do this? Look, since they are the same radius or radii, because we're talking about plural, take the compass and measure AB, or measure BP. Really doesn't matter how you do it, you already know. Now with the same, we need points of tangency, so that's what the perpendicular bisector allows us to do. Look, mark the circle in 2 parts. Now why 2 parts? Easy, because they want us to construct 2 tangents. If they only want us to construct 1 tangent, then you only make 1 mark here or 1 mark here. It really doesn't matter. Now it's over. We did it. Let me see now. Okay, boom. Go here, or you want to go beyond, you go beyond. Okay, I'm sorry it went over, but it's supposed to only touch one point. Now go here. Okay, and that's it. You have created your 2 tangents to a line. Oh my god, what the hell is inside? Oh, that's why. Okay, so these are your 2 tangents. Funny thing, and I'm gonna have to really do this with you. So the 2 tangents were from point P to the point of tangency. The guys are congruent. What are you talking about? They're congruent. Well, you measure the radius right here, right? Is the same distance from here to here. Now, when you mark the points right here, they were the same radius, AB. So it only makes sense that if you draw a line from here to here, okay, or from here to here, they're gonna be congruent. Okay, and this is a 90-degree angle. What in the freaking world are you talking about? Well, they are. They're 90 degrees. How is that? Okay. Remember something. This is nothing more than a circle. Let us create a diameter. Okay, and I am going to make this smaller so we could see what I'm gonna do. All right, so I am going to actually finish, okay, drawing the circle. The circle that I'm gonna draw is right here. Okay. Unfortunately, when I was creating the perpendicular bisector, I went overboard and I really went all the way, more than halfway. But this is your circle, right? So now, let me extend this point right here. Okay? Let me extend this point right here. Let me extend this point right here. Okay? We're Gucci with that. So this is the center of your, this is the diameter of the big circle. I don't know if you see. This is the diameter of the big circle, and it actually divides it in half. Well, if we connect this point with this point right here, and we connect this point with this point right here, okay? Yes, this is half of the circle, and this, it's supposed to be the point of tangency, right? Okay, now, this is a 90-degree angle. This is also a 90-degree angle. What the hell are you talking about? Well, think of it this way. This is an inscribed angle. It goes from the circle and it intersects half of the circle. And if we understand, if we have a circle, right? Let's say we have a circle. Let me draw it by hand. If we have a circle, okay, and this is the diameter, and there is, okay, and there is such an angle that, such an inscribed angle that intersects the diameter. Well, the diameter is half of the circle. The circle is 360 degrees, and the diameter, then it has to be half. So it's 180, a straight angle. Okay, and what do we know about the inscribed angle? That is half of the diameter. So this angle must be 90. Okay, this angle must be 90. This angle must be 90. Okay, so now you know. So because it cuts the big circle right here. It intersects the diameter. So it doesn't matter if you're talking about a small circle. It is still going to be the same thing. So then these angles are 90 degrees. So these are right triangle, these are right triangle. Okay? Got it? And these are radii, so they're congruent. Tangents, congruent as well. Now we have two sides and we have one angle. So side, angle, side. We're good. Alright? Alright then. Oh my God, we still have more. Okay, no problem. So what do they want? Construct the largest regular hexagon that will fit in the circle below. I don't need to tell you, but you already know how to construct a hexagon. And I don't mean by doing circles, sorry, not circle, but triangle, 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 triangle. So I'm just gonna make a mark right here and the point. So now, with the length of the radius, like this, now you're gonna go around. The same process as constructing an equilateral triangle inside a circle. Okay, that's it, right? Okay, so then now connect this point with this point right here, with this one right here, this one right here, this one right here. Oh my god, I really want to do something right now. Okay, oh, I got you. Okay, let's see now. Okay, hexagon inside a circle. Find the center of the circle below. Really? And then construct a hexagon? Alright, I don't have time for this. So we're gonna find the circle, the center of the circle. So we already know that we need a tangent here. Did I say a tangent? No, a chord, sorry. A chord, and we need another chord right here. Chord. And now what am I gonna do? Well, that's up to you. So do it. Construct the perpendicular bisector. Okay, I found the center of the circle right here. Now, what am I gonna do? Well, I don't need to draw a radius. We already know that from here to here is a radius, from here to here is a radius. So I'm just gonna take one of those measures. Okay, hexagon, sure. Go to this point, make a mark. 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 And I think I might have made a mistake. Let's see. Make a mark. 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 Why is not really fitting properly? And I can tell you right now, yours is not going to fit properly either, because, well, let's connect the points. But in reality, I guess that when I was doing the drawing of the circle, it did not. When I enlarge it, then it stopped being a circle. But the process is the same. So I'm not gonna stop. There you go. So that is your hexagon. 1, 2, 3, 4, 5, 6 sides. There you go. The beauty part is that we were able to do it. And is there anything else? Let me see. Check your understanding. Practice. Blah 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 blah. 1E. Sure, why not? So which illustration shows the correct construction of the angle bisector? Well, you should already know. So which one is it? Sure. Okay. Read it. So line segment AB is shown in the diagram below. Which two sets of construction marks labeled 1, 2, 3 are part of, and 4 are part of the construction of the perpendicular bisector of line AB? Perpendicular bisector, hello? Correct. 1 and 3, circle A, circle B, So you have to construct that. Okay. All right. So which statement must be true? So this is the angle bisector. We already know that. So which one of you has the right answer? ABD is half of CBD. CBD. This is not half of this, no. Congruent. ABD congruent to ABC. Sure, yeah. Right. ABD is equal to CBD. Alright, one step in the construction uses the endpoints of AB to create arcs with the same radii. So I have A and B, okay? And this is the same radii, so you know that this is going to be like that, this is going to be like that, okay? Now the arcs intersect above and below the segment. Yes, above and below. Yeah, sure, whatever, okay? What is the relationship between AB and the line connecting the points of intersection of these arcs? Come on. These, my friends, in parallel lines, these are called corresponding angles. Okay, two intersecting lines are shown in diagram below. Sketch the locus of points that are equidistant from the two lines. What is equidistant from two lines? Look at this, 4 angles. So equidistant has to be the angle bisector. So all I have to do is create the angle bisector. So arc here, right? Then measure the opening, like that. And then draw 2 more arcs right here. And that is my angle bisector. Then I do the same thing here. You know what? I'm gonna use the same arc for every single one of them. So arc right here, and arc right here. Measure the opening of the arcs, create the 2 intersections, and that's it. Alright? So that's the end of the class. And I'll be walking around checking what you did.